Okay, we've thought about some graphical representations of the data, these number of spikes per trial. We've computed, for example, the histogram. We've also looked at just plots of the number of spikes per trial and printed out the number of spikes per trial, different ways of visualizing the data. Let's now compute a couple of quantitative measures from the data, and the first one we'll compute is the mean number of spikes per trial. So we thought about this graphically in the histogram. We'd like to compute it now. And in general, to compute the mean of a list of values, we sum up all of those values and then divide by the number of elements in the list, or the number of values. So for example, we'll use these angular brackets to indicate the mean. So we'll use this symbol, angular brackets around n, to indicate the mean of n. What we're going to do is sum up the number of spikes in each trial. So the number of spikes in trial 1, trial 2, trial 3, all the way up to trial k. So we're going to sum up the number of spikes in each trial and then divide by the number of trials, k. And that'll give us the mean number of spikes per trial. We'll use this angular bracket notation to represent mean. And we can compute this quantity from the data. And I'll just tell you in this case, the mean is equal to 12.2. The mean number of spikes per trial is 12.2. And you might think about in MATLAB, how do we compute a quantity like this? The mean number of spikes per trial, if we're given a vector that indicates the number of spikes per trial. And we'll talk about this on Friday. Okay. Another thing to note is this single number represents a numerical summary of the data. So we've gone from this very complicated voltage activity recorded in vitro from a neuron that's been patched. This neuron's been placed in a petri dish. Voltage activity has been recorded from this neuron in multiple trials, 200 trials in this case. We then converted that voltage activity into a sprite train representation. Think of that as a series of zeros and ones. We then summed up and counted the number of spikes in each trial, and that gave us a vector, the spike count for each trial. And then we took the mean of that vector to give us a single number. So we've really compressed the data at this point from this very complicated voltage trace to one value, 12.2. So where is this number on the histogram, the spike number histogram? If we go back to our spike number histogram, we can indicate where is the mean, somewhere between 10 and 15. I've tried to indicate it here. The mean value is 12.2, right in the heart of this histogram. And that's maybe what we would expect. If we were to draw a trial at random of these 200 trials, we would expect to see about 12 spikes. We wouldn't be surprised at all. If given a trial at random of those 200, we pulled it out and we observed 12 or 13 spikes. Okay. So a related quantity we can compute from the data is the firing rate. And we'll define the firing rate, we'll give it this symbol little r, as the number of spikes observed per second in a single trial. So here's the equation. R, this is the firing rate for a single trial. It's the number of spikes in that trial, n, divided by the duration of that trial. We'll call that duration big T. So note the units of the firing rate are spikes per second, or hertz. Hertz is 1/2. And we can compute the firing rate for trial 1. How do we do that? How do we compute the firing rate for trial 1? Well, let's look at our data for trial 1. The neuron is delivered a stimulus. We record the spike train following that stimulus, and then the trial ends. And I'll tell you that the duration of that trial is 0.5 seconds. So we'd like to compute the firing rate from that trial. We need two quantities in order to do that. We need the number of spikes observed in this trial. So how many spikes do we observe? We showed earlier that n sub 1, the number of spikes in trial 1, is equal to 15. There are 15 tick marks that we can count here. 15 spikes occur in that half-second interval. We also need to know the total duration of the observation, which in this case, big T, is equal to 0.5 seconds, half a second. So then we're ready to compute R, the firing rate. What is it? It's the number of spikes in trial 1 divided by the duration of that trial. We found that the number of spikes is 15. We're going to divide by the duration of that trial, 0.5, and we get 30 hertz. So the firing rate of the neuron in this first trial is equal to 30 hertz. And as another example, I'll put this on Learning Catalytics for you to try. We can compute the firing rate for trial 2. So try it. Here's trial 2. What is the firing rate? We can also define the average firing rate as the number of spikes observed per second across all trials. So this is the average firing rate, where we're going to look at all trials of the data. And again, we can look at some equations. We're going to use angular brackets here to indicate an average. So we have the angular brackets around the little r. What is it equal to? It's equal to the, in the numerator, it's equal to the average number of spikes per trial, or the mean number of spikes per trial, which we computed earlier. It's this n in angular brackets, divided by the duration of the trial. So can we compute this quantity? We'll do that in a second. Note the units are again in spikes per second or hertz. We're dividing by time. So we have a time in seconds in the denominator. For these data that we've been considering, what is the average firing rate? And we'll get to this. So we'll be able to compute this in lab. We'll want to be able to compute the mean, which we found in the duration of the data. So you might think about, how would I compute something like this in MATLAB? The average firing rate, where we're looking at all of the trials combined, not just a single trial. So today we've considered, we introduced this notion of spike train data, and we looked at two measures: the spike number histogram, which is a nice visualization, and also the firing rate. On Wednesday, we'll consider three other measures: the interspike interval histogram, rastogram, and post-stimulus time histogram, and then we'll implement all of these measures in lab on Friday.